this is Mrs. Sharp, and we're going to go over Learning Target 5.3. If you were absent or you just missed a few things in your notes, you're in the right spot. So in Learning Target 5.3, we're going to define what an ionic bond is and how it is formed. Given the nature of two ions, we're going to predict the formula of an ionic compound. And that's as far as we're going to get on Tuesday, so that we're going to leave it at that. We're going to leave this last bullet point for Wednesday. So here we go. Here's the definition of an ionic bond. It's an electrostatic force that holds oppositely charged particles together, and we call those oppositely charged particles ions. So in the example of sodium, which is a +1, that's our cation, chlorine -1 would be attracted to that sodium +1, so there would be the ionic bond. It's just the force that keeps them together. So that force of attraction is called an ionic bond. Ionic bonds are always going to contain at least one metal and one nonmetal. So sodium, you can see, is on the left-hand side of your stair step on the periodic table. So there's your metal, and chlorine is your nonmetal. You can have more than one nonmetal, but you'll always have at least one metal. The difference in electronegativity between the metal and the nonmetal must be more than 1.7 to be an ionic bond. So I would encourage you to mark this on your periodic table on the back side. If you flip over onto the back of your periodic table up towards the top, you have a little table that says % ionic character. And it also says difference in electronegativity. And if you would look at that table, and between where it says 1.6 and 1.7, if you were to draw a really heavy line between those two numbers and put ionic, you will know that everything that has a difference in electronegativity between 1.7 and up is considered to be an ionic bond. That would be good for later. Here's a funny. An ionic compound is defined as a compound that contains ionic bonds that's made up of ions. So it must be neutral overall, which means if sodium has one valence electron, it would want to lose one valence electron to become sodium +1. We've gone over that a lot. And chlorine, with 7 valence electrons, would like to gain 1 electron. And so what we haven't talked about yet is where that 1 electron it gains comes from. So that electron can't just come out of thin air. It has to come from somebody else who's gotten rid of it. So the sodium and chlorine example works really well because sodium has 1 to give up. Chlorine would like 1. So now we've got chlorine with 8 and a -1 charge. Sodium giving the electron, chlorine taking the electron. And chlorine has a really high electronegativity. Chlorine's electronegativity is 3.16, which means it really, really wants another electron, and sodium's is really low. So I don't know exactly what that is, but if you took 3.16 and subtracted sodium's, you would get something that's greater than 1.7. So sodium chloride with a +1 and a -1 charge is neutral overall. And sodium chloride is represented by a formula unit, which is like a molecule, that has 1 Na+1 and 1 Cl-1. So we write the formula of the formula unit by taking how many of each ion there are. There's nothing indicated about the charge here, just how many of each ion. There's 1 of each, so we say Na, Cl, 1 of each. Here's another example. Calcium has 2 valence electrons, would like to become calcium +2. Fluorine would like to pick up 1 electron. Calcium has 2 to give up, so it only needs to give fluorine 1. So we have a problem here. The oxidation numbers have to be neutral overall. Right now we have an overall +1 charge. But we can fix this if we have 2 fluorines. Calcium can give 1 to fluorine and then 1 to another fluorine and make them both happy. So if you'd have 2 Fs, then overall we would have a -2 charge to balance out this +2 charge. So one formula unit is not going to be CaF. One formula unit is going to be CaF2. One formula unit has one Ca and two Fs. So notice how our charges balance out. Positive 2 and a total of negative 2. Whenever I have polyatomic ions present, that creates kind of a different situation. Let's take aluminum and hydroxide. So right now those two are not equal but opposite. I've got an overall positive 2 charge right now. So I'm going to need 3 OHs total. So I would get a negative 3. So to do that, so I've got one ion with a positive 3 charge making plus 3, and 3 ions with a negative 1 charge making a negative 3. So in order to do that, I'm going to need to use parentheses to separate it. So I would write Al parentheses OH3. If I didn't do that, if I just wrote Al OH3, it would only look like I needed 3 hydrogens, not 3 of this whole thing. So we put it in parentheses. We don't change anything about this. Just keep it in parentheses and put the 3 outside to show that there's 3 of everything inside of here. So one formula unit is going to contain 1 aluminum cation and 3 hydroxide anions. And this is what we just said, that this can't be right because it means 1 Al, 1 O, and 3 H's. What we really want to say is that we have 3 OHs. Keep going here. Here's another example. Seriously, it's that important. We've got Fe, ic version, so plus 3, and S minus 2. So in order to do this, we would want to find what's called the lowest common denominator if you're in math. So we want these charges to balance out. So in order to do this, we need to have a positive 6 and a negative 6. So we would need 2 Fe plus 3's to make positive 6, and we would need 3 S minus 2's to make negative 6. Remember, these are the numbers that I want to use to write my formula. So I would write this as Fe2, because I need 2 of them, and S3, because I need 3 of them. So one formula unit would have 2 Fe plus 3's and 3 S negative 2's. Okay, so that's it. I hope that helped. We'll practice some more in class. See ya.